So welcome everyone. I think we can start. Please welcome Pavel Odvody, who will talk about distribution profiling and code analysis.
Hello. Thank you very much for the introduction. So for today, I prepared to talk about distribution profiling and code analysis. So why I prepared this talk? For over a year, I have been working at Red Hat with Docker, containers, and all that stuff. And I realized that there is some tooling missing to make the job really easier. Because suddenly when you try to, for example, Dockerize something or put it into the container, you realize that the assumptions about what is default in the system are quite different from distribution to distribution, and that more often than not you encounter very difficult and not helpful error messages to solve. And because I don't like reading long error messages and solving them manually by hand, I decided to write some tools about which I'm gonna to speak about today. So first we will start with nomenclature, what it actually means, the distribution profiling. I guess that everybody is familiar with code analysis, so I will not delve into that, but then I will go into how dependencies are handled in the different distribution systems, what it means for a dependency to be transient. I will also cover some built-in packaging systems and problems there and how to solve them. So, nomenclature. Distribution profiling is a process of figuring out how a particular software unit fits into the target distribution of our choice. It can be really Fedora, CentOS, RHEL, you name it. Yeah, there are also other distribution mechanisms besides Fedora, RHEL, or RPM in general. Each language nowadays has its own package manager. For example, Python has pip, Ruby has gems, JavaScript has npms, and now we have to figure out how can we make all those cooperate nicely together. Because, for example, one way to get a package you want installed is directly via the upstream mechanism. So, for example, pip install 6. But we can also get the same package from our distribution. So it's kind of a problem there. But there is a much bigger problem. Because, for example, if we try to install some package that actually depends on something that should be in the system already, then we are in problem because, for example, some package may need GCC to compile some native dependency, but like I said, for example, in Docker and the containers in general, you are working with a really minimal build route. So there isn't really much of the thing. So GCC is not there, and a lot of basic tools that are generally considered as default in the system, they are not there too. For example, which, tar, find, and it goes on. So let's take a look how, for example, the Python ecosystem looks like. We have many different packages. There are just some I handpicked. The arrows show the dependencies between the packages, and this is like ideal world because if you want to, for example, install Django, you install Django and it drags in several other dependencies like psycop, G, 6, and there is actually much more dependencies, but I didn't want to clutter the image so much. This is nice and everything works, but then we realized that we are, for example, working with a system that doesn't have GCC installed, and then we realized that psycop-G actually needs GCC to compile its native dependency on Postgres. And that is a problem because it's not there and the Python has no idea from where to get it. So there is also other part of the system that we work on, and that's the ecosystem of the distribution that we are using. And there is all of that packages that we need. There is make, there is GCC, Postgres devel, libpng devel. So we need a way to essentially do this. And this is important because otherwise we are not able to use the software at all, because when we download a package, want to use it, it's not actually only that one package, but it's a complete sum of all the dependencies and all the code that contributes to that package. So at this time we call them transient dependencies, and why we call them transient is because they cross the boundaries of the specific ecosystem and need to use packages from a different ecosystem. So, for example, make, GCC, etc. have to be provided by the distribution, because if we lived in a world where, for example, Python has packaged GCC, make, and all of that, then it's quite likely that Ruby would do the same, that they would have their own GCC package, JavaScript would do the same too, and if we used all of those languages and systems, we would suddenly end up with like 10 different versions of GCC on our computers with different versions and managed separately, and that is a problem, and we don't want to do that. We want to use packages that are provided by the distribution that we trust and use, and the rest has to be worked out. So, yeah, what do we use to do this particular mapping? So, this problem could be split in two, and one part is actually searching for header files that are needed to compile the native extensions. That means going through all the C, C++, source, and header files and figure out what are their requirements, and find which package from the distribution provides these requirements. So for that, first, built-in packaging systems mostly work by means of some magical file that you just drop into a folder, and suddenly all files and directories that are like recursively down beyond this one turn into a package. Examples of that would be, for example, configure AC for the autoconf, make file for make, package JSON for JavaScript, setup py for Python, etc. Like I mentioned, most of these built-in packaging systems are really recursive in nature. That means that you, for example, execute the outermost make, and it will build all the other packages that are below that one. The good thing about some of the packaging format is that they are declarative. That means that you can actually parse them. They are, for example, JSONs or XMLs that you can simply read out what is there. But the other packaging formats are highly imperative. So for PyPy, the setup Py, it's just a Python script that just calls the right function. So analyzing that is actually, it's tricky. And I will talk about that later. So first, the headers. I wrote a tool, it's called Feathers. It's a term which I put together from Fedora, headers, and search. And how it works, it recursively scans the directory for C/C++ files. It finds all the include statements that are there. It uses regep, regular expressions, because the thing is that the include statement in C or C++ is actually a preprocessor thing. It's not a C code. It is parsed by the preprocessor, and the code from the particular file is simply included in the source file that includes that. So, and I really didn't want to, really didn't want to write like some emulator of the preprocessor so that I would be able to decide, because the preprocessor allows you to do many different things. It allows you to include some files based on some conditions, but I don't really want to care about that, because these are like build time things. They depend on the environment. So I want to get like all the information I can. So I'm using regular expressions right now to get the include paths, and then the step 1.3, because we can also say that there is like a canonical source of header files in the Linux distribution. It's /user include. And so if you find out that there is some file that needs, for example, png.h included, we can simply prepend that png.h with the standard include path and try to do a repo query against the RPM database to figure out which package in the distribution provides the particular devel library. Feathers is actually split into server and client part, because with repo query we can actually query only a single file, and the bootstrapping of the repo query takes about 1 second. And because, like I said, that it's working rather brute force, I'm not analyzing the preprocessor directives in any way. I just need to know what are all the possible includes, and there is many of them. So scanning a mid-size project would take a very long time. So I wrote the server part, which can do like a repo query in bulk. You can take like 15 different files and query the Feather server with that, and it will give you answer in a second. Yeah. Some details about the server. If you have ever tried to work with the YAM metadata, they are distributed in like 2 formats right now. One is a SQLite database, and the other one is XML. The databases, there is actually always more than one database, because there is like the base repository, then there is the updates repository, and there can be much more repositories. So the server part is made to work with that. Currently, Fedora and CentOS repositories are supported. Because I'm a lazy person and I like GUIs. You know, I just lean back in my chair and click things through. I created a tiny front end and administrative GUI for that. But the client part, which is a CLI, communicates with that via Flask REST API. The Feathers server also has associated systemd service files, so it can start nicely as a system service. So that would be about Feathers. Yeah, and as a result of these decisions, it can search thousands of files in a second, which I will show later in the demo. Then I wrote another tool, which is called Mercator. It is a build package mapper. It scans the directory tree again. It tries to find all those different magic files set up by, again, makefile, and it actually tries to establish like a graph-like notion between the files. So you, for example, know which one you should build first, and if it fails, where you can move on. It also works for Go packages, because in Go, the definition of a package is basically just a random folder with Go files within that. Yeah, there are two kinds of output from the Mercator. One is like a complete graph that you can use to, for example, execute the outermost build system in the graph. And there is also a flat output, which you can use to get quickly a list of needed RPMs that you need to install. So, you know, if there is makefile, you will need a make. If there is a configure AC, you will probably need autoconf, etc. The tool can provide you with a JSON or a tree-like structured output, so you can actually wire that to some other tooling to automate some processes that you may want to execute on top of that. Now, the interesting part, setup by gemfile, etc., are all imperative Turing complete specifications. And that is a problem. For example, if we want to get the list of dependencies, we have to work really hard to get that list, because we have to make the tool understand the set language and somehow pull the information out of there. So, what is used in Mercator for analyzing these packages is that we use static analysis, and for that, for different libraries, or for different languages, we use different libraries. So, for example, for Python, we use Redhawk, which is a Pythonic library for doing static analysis, and it's nice in the sense that it allows you to basically execute an XPath-like queries over the source code. So you can actually query very quickly the source code. For example, find me a class or find me a module that defines this particular function in that particular context. For analyzing Ruby, we are using Yart, which is, I guess, it stands for yet another Ruby documentation tool. So originally, that tool was created to actually create documentation from your source code, but there is actually a big overlap between the efforts, because to actually produce useful documentation and all of that, you need to analyze the source code to a certain level. And that level is just enough to also give us information about dependencies of the package unit, and it can be, again, dependencies within the ecosystem itself, but it can also be the transient dependencies that we will need to figure out from the distribution. And yes, for the rest of the build packaging systems, there is just a set of regular expressions because, makefile, it's just a shell script, basically. The same goes for autoconf and C and C++. Yes?
For autoconf, there is actually a tool that's called automate with a form instead of the A, so autom for
Mm-hmm.
and that's basically what automate uses to parse configure.ac.
So it can give you declarative.
It can give you for every invocation of some macro,
Mm-hmm.
it can give you the parameters of the macro.
Mm-hmm.
After expanding everything. So for example, you can use it to find the PC files if you create
Mhm.
the pkg check package macro, or you can use it for header files with the check headers, search libs. In the end, almost all of autoconf is just cut and paste, except
Mhm.
for 4 or 5 important macros. Just trace those and you will get all the information from there.
That sounds very good. How was the tool called again?
So just do rpm minus qf
Uh-huh.
minus ql autoconf and you'll find it.
Uh-huh.
It's called automate, auto M40.
Uh-huh.
Unfortunately, it doesn't have for like minus L flags in the make files. For that, I agree that you just.
Well, thank you very much. I will definitely look at that and I will try to incorporate that into the Mercator package because it sounds like, working with regular expressions, it's just something you write them once and then when something changes, you have to rewrite them, delve into the code. So that would be really amazing. Thanks for that.
Make was something that gets close, but it's not exactly what you want.
Mm-hmm.
There is an option to print the variables, all the definitions of the variables in a make file. It's make minus print database, something like that.
Mm-hmm.
And it needs a make file, so it doesn't work very well with the makefile.m and makefile.in, but maybe some cases it can work.
Yeah. Thank you again.
No problem.
I will take a look at that. Yeah. So now for the demo part, I have prepared first I would like to showcase the tool that uses Redhawk to analyze. Yes, my username is funny. I would like to show you a tool that processes setup.py in Python and gives you back a JSON output of what's in there. First, how it actually works, because like I mentioned, setup.py is imperative format. It can do really pretty much anything, and as I analyzed more and more setup.pys, it is true that a lot of stuff happens there. Files are read from the disk. That description is then used to describe the package itself, and it's not nice, to do just the static analysis on top of that, because you would actually need to also a lot of code emulation to get to the thing that you want. So I wrote this setup mock, which uses static analysis to find the setup call of this utils package, and it actually replaces this call with a mocked up method that just prints out JSON. There is some steps that need to be done because, for example, you cannot serialize any Python object into JSON. So I have to strip several parts of the setup.py. But the things I was actually interested about were the extensions, because if the Python package needs to compile some native extension as part of the installation, it's actually mentioned somewhere in the setup py, so it can be found what the Python package will be attempting to do at the install time. So I will execute setup mock over my favorite Python package, which is Pillow. It's a Python library for manipulating images, opening JPEGs, PNGs, rescaling, or doing a lot of stuff. If you've ever used some Django project, more than likely it was depending on this particular package. When I execute it, I get back this plethora of information. What is nice is that we can actually see that the keys and the data correspond with what's in the setup py, and here on top is also the ext modules key, which stores the information about which native, which source file needs to be compiled into a library so that the package can work. If we take a look how the setup py actually looks like, it's actually a lot of code. Some files like readmes are read actually from the disk, so the data would not be there. So this is not really interesting. Yeah. So if we take a look at what the setup mock does, one of the interesting things about mocking the setup call is that Python is actually, the scope of the different blocks is defined by source code indentation. So when we place the mocked up call back into the code, we need to also make sure that it matches the white space that was defined at the particular place in the file. Here is the code that's like the mocking part. Again, the nice thing about the setup call is that it's actually very generic functions that just accept key value parameters. So we can use that. We can use the dictionary representation of that to simply output back a JSON. Here is actually the manipulation of the syntax tree, where we are looking for a node of the type call function, and we are looking for a node that calls the specific function called setup. And once we have found that function, we can inject the code back into the file, but not into the original file. We create a mocked one in the meantime, and then we simply execute the mocked file, and we will get back a JSON, because the only thing that the mocked setup function does is to print the formatted JSON. So that would be one example. Now, which headers and libraries you actually need to install Pillow? Okay, so we will use feathers to find out. No, I can't type. Okay. So first I need to figure out if the server is running actually. Oh. Okay, so the server is running. Now I can execute the feathers client. I actually, because it's not using the server by default, it defaults to a repo query. So I need to point it to the correct server, which is just running locally on a port which defaults to the Flask, and I will also tell it to give me back information for a particular release 23 of Fedora. Yeah. So this is the set of packages that we would need to install to get the native extensions of the pillow to compile. As you can see, there is some because the native extension actually creates a Python object. It needs the Python development libraries, and the Python development libraries are provided by 3 different packages. It's Python 2, Python 3, and there is also PyPy. So all of them are like in the output. I really didn't figure out how to tackle this problem. For example, I could take a look at the particular machine and what's in there and try to figure out if there is, for example, only Python 3 installed. I could simply choose the Python 3 devel and throw the rest out of the window. But actually, it's not that easy because you can have multiple Pythons installed on the system. So I'm just at the moment outputting all of the packages that were found. And that means that there is, more Pythons than you need, but you can simply just remove it from the output and not use it. Yeah. The second tool I wanted to showcase, I could actually try now and try to install the package in a container, but I guess that we don't have that much time, and the network would be kind of slow. So maybe I'll get back to that later. Now I want to show you Mercator. Okay, I haven't installed it. So what can Mercator do for us is that we just give it a target path to scan, and it will go recursively through all the magic files and provide us with some reasonable mapping and output of what all is there. So again, if I execute it on top of the pillow package, I will get back that there is some make file, that there is also some docs file, that there is some make file to make the documentation, and that there is also a setup py. Because it's files, they have no children nodes, but as we can see, they have different height or depth in the graph. What we can now do is that we can also get back, like graph-like mapping, where we see that the one make file is actually a children of the top make file. And there is also this JSON output possibility, which will tell you what all projects are there. This was a rather easy example, So let's try it, how it tackles a much bigger beast. So for example, systemd. We see that there's a lot of makefiles mapped at different levels. And we can also see that all of those makefiles are actually children nodes of this configure AC, which was used to generate those makefiles. And yes, this is actually the state of things after I have executed the autogen sh, which is a script provided to build the systemd, which basically preprocesses all those makefile ints that are there and replaces the macro within them. We can also try to execute it on top of something that's much bigger. Unicorn. I'm not sure if I got some bigger project right here. Okay, so I guess that I can showcase now, I can try to showcase now the installation of the pip package of the pillow package in the container. So the first thing I will summon this magical command back to get back OK, because I want to use the output. Oh. Okay. Now let's try to start a Fedora 23 container. Come on. Okay. And let's do a pip3 install pillow. Oh, the network is live and kicking. That's well. And we will see that once the package is downloaded, pip will try to install it and hell breaks loose because JPEG is required, blah, 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 blah. Actually, there is no way to disable it right now. So the first thing that we need is that because Feathers takes care only about the header files, we actually need to install the GCC manually. And we are also gonna need a package called Red Hat RPM config, which contains some linker settings that are needed to build the extension. So yeah, because I'm working from a fresh image, I need to download the repository data right now. And after that is done, I will also need to install all of the packages that were found in the previous step by Feathers. But what I want to show you is that installing GCC and the RPM config is not enough because it will still fail. You know, one could assume that it failed because there was no GCC, but we will see that it fails exactly at the same step. Or we will not see. Let's hope that we will see that. Oh, I'm out of time, so if anyone has any questions.
Where can we find the slides?
The slides, I guess they will be at the DevConf site somewhere. Is that right?
They should be. We are taking slides from all presenters, and this will be available for sure.
Okay.
Any other question? I would like to remind you that by having a question, you can get a really cool scarf like this. It's cold outside, so.
If I paid attention well enough, the tool that Feather's tool, or whatever the name was, it tries to concatenate the found C header files with /user/include. But what about projects that store those header files in different directories and use package config to supply -i option to GCC? It's not covered, right?
It's not covered, but this particular area is supposed to be handled by the Mercator, which can analyze the configure AC to figure out on which packages from the package config it depends on.
Okay.
Is there any last question? I guess not. So thank you, Pavel, for your presentation.